Yeah, very good. Yeah.
Yeah, we already started after finalizing this Congress, so we will start to announce the fourth one as well for 2023. So we will inform you as well.
Yeah. Please, yeah, I appreciate your invitation. I will be ready for that, and for sure, the pandemic will be finished at that time. So it's good chance to go and see, our colleagues, meet with you and the others in Italia. It's Italia, as you said, is the best. I didn't see Italia before, but I know it is the best place in the world, honestly. And
It is really,
also good to do some collaborations with the other colleagues also.
yeah. So I keep my fingers crossed.
Yeah, we hope.
Yeah. So how
we
is
hope that we hope that
yeah,
it's
yeah, yeah.
all right. It's been 2 years, with this pandemic. But now in US, the things going is much better. We have, around 50%, in-person meetings. So I hope, the end of this year, the next year, we will back to the normal. Even now in our education here in the university, we go back to in-person meetings, and now it's the things, it's much better, honestly. Yeah. So
I think this I mean vaccines are making life easier for all of us.
yes.
But in Turkey now, the daily cases are really very quite high. So we have
I see.
around 30,000. I mean daily cases. So
Oh,
this is still very high.
very high.
But the vaccination is going on. I mean taking places. So people are getting more and more. I think reliable on this vaccination. But some people are against vaccines. I really don't understand them, but really, yeah,
Even here, same thing, Dr. Sehat. Even here in US, I have many friends, also they didn't took the vaccine for some reason. I don't know why, but it depends on them. Yeah.
but I think we have to be careful.
Yes, I mean,
Yeah,
yeah, the risk is high. The risk is not. The risk is very high, and
yes, we have to take our responsibility, and we have to respect others' life.
I
So
agree with you. This is important. You are right. We have to do that. You know, we have restrictions here also. For example, mask. It's not mandatory, but still, we appreciate every student, anybody, any colleagues who wear mask.
mm,
But it's not mandatory, honestly. So we
the,
hope, Dr. Sehat, we hope everything will go back to the normal. I hope that.
yeah, still the mask is mandatory here. So, but we
In
have
our place, in Turkey, it's mandatory.
yes,
Yeah,
the
here, no. Here, after, I think before 2 months, I'm talking here in Texas mainly. They announce, it's not mandatory I cannot say for all Texas, but most of the places,
mm,
it's not mandatory. School here is not mandatory. If you go just for example, some visits like doctor visits, these things, clinics, they ask for masks. But in general, markets, any other places, schools. Yeah, schools, also schools is not mandatory colleges, universities. It's not mandatory, you know.
The all places are mandatory here. The
Yes.
schools, colleges, universities, because the daily cases are really quite high. And also the vaccination ratio is, we have not reached as the top level. Maybe this is the main reason. So 30,000 daily cases, actually quite high.
In
So
Turkey?
we have to reduce this number.
So in Turkey now, 30,000 cases daily?
Daily, yes.
Oh, it's too high.
It's too high. Yeah, it's too high.
It's too high. And the vaccination is available?
Yes, it's available. It's free, but
very good.
But I don't understand why people don't want it. So it is free of charge, and it is Pfizer BioNTech, but still, you know, well, when the first vaccine was found, say about maybe 300 years ago, so the people against at that time for the same reasons. So after 300 years, the reason is not changed.
Yeah. In fact, you know, the vaccine before a year, it was, you know, not easy to get it. Yeah, but now it's available, so it is good opportunity to everybody to go and take this vaccine and to protect him or herself and with the family, with all the others also. But still, here in US, I think we are going to 60%, more than 60% people they already vaccinated. So this is good ratio.
I think you started the boost job as well.
Yes.
Or third one, I mean.
Oh yes, yeah. We start. I already took the first shot, Moderna, the second shot, and they didn't ask me honestly to take the third one, but my wife and my kids, my son, my daughter, they took Pfizer, 2 shots, but they asked them to start the third one.
I think in November, so we will be asked for the third one as well. So we have mainly Pfizer and BioNTech. So I mean Turkey used first in the Sinovac, but now I think nobody. I mean people mainly prefers Pfizer and BioNTech.
Oh yeah. So what type of vaccine you have in Turkey? You have Pfizer, I think. You have another types.
I think the mainly Pfizer. So the second one is Sinovac, and I think end of this year, so we will have Turkovac, I mean Turkish scientists developed. And so end of this year, so we will have it's called Turkovac, and so they are planning to I mean distribute other countries free of charge as well.
Yeah. This is good step. You know, we hope to control this virus as much as we can, then we can protect ourselves and the others. You're right.
You know, we affect each other, so we have to increase the vaccinated people ratio, not only in our countries, but in other countries as well.
Correct, Dr. Saad. Yeah. I hope, you know. But you just surprised the cases in Turkey. It goes to this number, 30,000, and I thought it's less.
Unfortunately, it is. Yeah. Yeah, I mean, because of this, Professor Recep sent me a text and he said that please ask Professor Azavi to wait for me. So he said he's coming soon.
No problem, you know. No, no.
Yeah.
I can. I'm at the university. I came to my room, and we are enjoy your talking with you, Dr. Sayat. I appreciate your time. Also, I know you are busy.
Thank you very much.
It's
Thank you very
okay.
much. Yeah. For
Yeah.
accepting and for sending the your I mean for submission your papers as well. So actually, where are you from, Professor Azavi?
I am from Iraq.
Or komşu?
Yes.
Yeah, you know komşu?
Ben geç mi kaldım?
No.
Dr. Rajab, how are you?
Hey,
Good, very
Dr.
nice.
Azavi. How are you, Dr.
Good,
Azavi?
good, Dr. Rajab.
I am really
Nice,
sorry.
nice, nice beard, nice mustache. It's really nice.
See, I'm in my own country, so I'm enjoying my life. This is the best place in the world to live. So
Yeah.
I'm really sorry, Dr. Azavi. I was also hosting the keynote speakers session. It was a little longer than I expected, so I had to finish that one first, and then I joined here. I'm sorry for this delay.
No,
I
I
hope.
appreciate it. I know you are busy, Dr. Rajab. And Dr. Sayed, in fact, we have good chat with him.
Yeah.
Yes.
He really consider you as his brother, honestly.
Yes, I know that. Yeah, you're my brother as well, Dr. Azavi. I really like you, and it was very nice to meeting you. And I'm.
And we miss you
hoping
here,
that-
Dr. Rajab. We miss you here in our university. Our best
Thank you.
professor, you know.
Thank you.
You left
Thank
us
you.
soon.
Thank you. Who knows? You know, we don't know what life is going to bring us in the future. We'll see
We hope
what
to meet
will happen.
again.
Yeah.
We hope
Yeah,
to meet
yeah.
again.
We never know actually.
Yes. So, Dr. Azavi, here's the situation. You are the only person in the Congress who is going to present in English. That's why we have decided to put you in one session, all your work in one session, so that you can speak of your work one after another in any pace you want. It's up to you. What we're doing here is that we are having this presentation in YouTube. However, at the same time, we are also live streaming it on YouTube, Twitter, and Facebook channels of our organization. So lots of people are going to be watching this video through the other channels, not here. This platform is for the session chair and the presenters and the Congress organizing team. That's why we don't have many people here in our platform, but people are watching it on the other means, other platforms. And it's being recorded, and they will be able to watch it later on the coming days or months whenever they want. So you will be on record forever. So be careful.
Professor Recep, I already invited Professor Azavi for the next one, for fourth one.
Inshallah.
And he accepted. You know, we organized this, Congress in Antalya.
Yes.
But due to this pandemic, we organized this on online Congress. But for the next one, 2023, so we will have this Congress in Antalya. Inshallah.
Inshallah.
By keeping my fingers crossed.
Okay.
And he already accepted. So he's going to join us in Antalya.
Yes, he's a friend of Turks. He has lived in Turkey. He knows Turkey. He knows Turkish people. So I'm sure that he's going to enjoy Antalya as well. That's a good offer, Dr. Azdavi. Don't miss that. And
Yeah.
I will be happy to see you and to host you there as well, inshallah. Okay. All right, Dr. Azdavi, without further ado, it's your time, and you can use share screen and you can start your presentations whenever you feel like.
So I can go one by one,
Yes.
as you said, or I can go with anyone. For example, start with second or third or one
it's
by.
Up to you. It's up to you. Whichever you like to do that. What I will do is I'm going to keep track of the other channels to see if there is any questions regarding your works. If there is any questions, then I'm going to stop and ask you those questions. If
And
not,
I have 15 minutes.
You can continue.
15 minutes for each presentation.
Yes. Yes.
Okay. Yeah. Yeah. I will start. I will
Please.
see what I have.
Yes. Yeah, we see that. Yeah, we see your presentation.
Yes, Dr. Rajab.
Numerical simulation of SFRC columns with openings under uniaxial bending. Yes.
Yeah, in fact, this is the first research which I did here in the University of Texas at Arlington, a numerical simulation for steel fiber reinforced concrete columns with opening under uniaxial bending. The problem statement is how does the install opening and holes in reinforced concrete members allow access for surfaces such as pipes for plumbing and electric wiring effects on its ultimate strength as a projection of pipes outside the columns will affect the appearance of the building. Also, how does the volume fraction of steel fibers in concrete affect the column behavior? And does finite element modeling of composite concrete columns provide results close to the experiment? In fact, we did the experiment. I did the experiment by myself, and also we compared the experiment results with the finite element modeling. And we keep just in our mind, if we have some openings inside columns, which is in general, we have it as an access for drainage in some chemical buildings, an access for pipes, has some harmful material. So how that will affect on the column strength, especially the ACI code, in fact, even ACI code 31819 doesn't cover this issue, and they didn't have a solution for columns with opening. We have to go with the regular method. So the outline of this research is identify numerically the behavior of steel fiber reinforced concrete hollow columns under eccentric loading, and also validate the numerical model by comparing results to the experiment data. This slide shows us the role of steel fibers. If we provide the steel fibers and mixed with concrete, the steel fibers usually increase the tensile strength mainly of the concrete composite, and increase the modulus of rupture also, make the section more ductile compare with concrete without any fibers, and also control the micro cracking and the crack width. This is the, I'm talking about the experiment work. This is the specimen I propose to do it. I have column here, and I just make extension here to provide eccentric load to this column and to provide uniaxial bending. And this is the section of the column, and I have hole inside. This hole is a variable hole. I use two ratios, 10% hole area and 20% hole area with respect to cross-sectional area. And I have these reinforcement. In fact, I designed this corpel, this part, carefully to prevent any shear failure will be developed at this region. Just to make sure that I have failure in the column itself. This is the nomenclature of column specimen. So I prepared 10 samples. One sample hole or opening inside column 10%, the other one is 20%, and with different percentage of steel fibers. First sample is a solid without any hole, just I use it as a reference. And the second one with 10% hole, 0% of fiber. And the third one, as we see, it's 0.5% by volume with hole, 1% by volume with hole, and also 1.5% steel ratio by volume with 10% opening or hole ratio. And the other group, same thing, but I increase the hole, make it 20% just to see the effect of providing or increasing the holes inside the column. This is the steel fiber I already used, and I already ordered it here from US. And it's galvanized steel fibers. And this is the properties of this type of steel fibers. I did a mix design based on the ASTM C192 and also C192M, providing these mixed properties. Then we start produce the concrete. First of all, we check the slump. As you see, slump without any fiber, it goes to around 8 inches with 0.5% steel fibers. The slump is reduced, as we see. 1% is more reduced. 1.5%, the slump is around 4 inches, which is, I can say it's accepted in the practical work. Yes, the workability will be tough, but still the strength will be high. After preparing our specimens, we put it in the control room. In our lab at UTA, I prepared samples for flexural test, samples for compressive cylinders for compression test, and cylinders for split tensile test. These are the samples. This is for flexural test, this is for compressive test, and this is for split tensile test. So after 28 days, we start tested. First of all, there is no a formula how to calculate the modulus of elasticity for mixed concrete with fibers. The ACI code gives us one formula, we can use it, but without fiber for plain concrete. That's why I test the modulus of elasticity, and I find out the modulus of elasticity experimentally by using strain gauges and apply load and have the load deflected shape. This is the compression test to find the modulus of elasticity. We have load cells, we have strain gauges, and also it is connected with the strain software, as you see. and this machine is the compressive test machine. We apply, in fact, around 400 pounds per second as a testing load, and this is the curve we produce for this type of concrete. This for 0.5% ratio, steel ratio. Then we make a regression analysis to find the modulus of elasticity for this type of concrete. Also, we finished the compressive test based on the ASTM C39. These are the cylinders we prepared by 8 inches. This is the failures we have, as we see, with the 0 fibers. We have a cracks here. It's really noticeable. With 0.5%, we have failure, but we don't have that much cracks. This is 0.5%, sorry. And this for 1%. And for 1.5%, as we see, we don't have that much cracks. That's why the steel fiber will make the concrete ductile behavior instead of brittle material. We see the increase in compressive strength. Yes, it is not too much an increase between 1% and 1.5%. That is expected because as we increase more, put more fibers, the compressive strength will not be increased. This is the flexural test, modulus of rupture. Also, we have another machine. We apply 4-point load and find the modulus of rupture for different types of mix. With 0% means plain concrete without fibers, 0.5% steel ratio, 1% and 1.5%. As we see here, we have a brittle crack because we just have plain concrete without fibers. But once we increase, we put fibers, we see there is some ductile behavior, and we don't have that much cracks. With the 0.5%, we have cracks. It's noticeable, but with 1% and 1.5%, we have a crack. It's failed, but still the behavior is ductile. This is the modulus of ratio, the modulus of rupture results. And as we see, there's a noticeable increase in the modulus of rupture for concrete with fibers. Also, we did the split tensile test, as we see. We prepared 6 by 12 inches cylinders. And this is the split tensile behavior for different types of mix. And these are the results. Also, we have really, we increase the tensile strength of concrete is really increased once we provide the steel fibers to the concrete. These are the specimens prepared at the UTA, University of Texas. This is the column, and these are the holes. I put styrofoam inside, just represent the hole, and this is the steel cage. After casting the concrete, these are the specimens. Then I prepare the instrumentations and the test setup for these specimens. I use load cell with LVDTs, as we see here, to check the deflection at mid-height, and the eccentricity. It's 0.75, the eccentricity ratio, column depth ratio. I keep it constant. This eccentricity will provide a moment to this column, as we see here. So I test all the specimens I have, and these some results for the crack pattern of the tested columns. So as we see, we have different strength, different crack pattern. Once we increase the steel ratio, the behavior is much better. and can resist more load. The capacity is increased also. I just show you here. This table shows us the cracking and ultimate load for the tested columns. So as we see here, group 1, which is 10% opening ratio. If I have column with 0% opening, 0% fiber, can carry 187 kilonewton. This is the cracking load. If I provide whole 10%, and I will provide steel fiber 0.5%, as we see, I can get the same result. So that means if I have hole inside columns, I don't need to increase the column size. I can keep the column size same, especially the architect doesn't like to change the column sizes and use same size for all columns in the structure. So I can keep the hole, but if I provide some fibers, that will increase the strength, as we see here. Also, the ultimate length, the ultimate load is increased also. The other group also, as we see, if I increase the opening ratio, the strength also increased. Then I did the finite element analysis using Abacus software. So I modeled the strain, the steel cage, and the concrete. We use concrete block element for the concrete and bar element for steel. So after assembly and run the analysis, we use also concrete damage plasticity for the analysis. We have the results. I can say it's close, not same 100%, but it's close to the experiment. The maximum stresses, as we see here, it's almost same locations. The other also, we have maximum stress here, which is around 91, 110. So this region almost carry the most stresses. And also I have failure here at mid-span, mid-height. Also I have also stresses at the mid-height for the finite element analysis. This is the this table shows us the results comparison between the experiment and the numerical analysis. So I have around 6.2% as an average. The difference between both methods, which is I feel the modeling is fine, give us good results. For the other group also, I have around 6% difference between two approaches. So the main conclusions, in fact, I can draw from this research that adding steel fibers will increase the hollow reinforced concrete columns, first the cracking, and also absorb more energy and prevents premature failure of concrete, and also increase the buckling strength of the column itself. Also, the cracking load of specimens, I noticed from my research, the cracking load for specimen C51 means 10% opening with 1.5% steel fiber, and increase around 2.4 times the cracking load for same specimen but without the steel fiber. And for a specimen with 20% opening ratio and 1.5 steel fiber, the cracking load increased around 2 times the same specimens without adding any fiber. This remarkable improvement of strength could allow hollow concrete column strength with the steel fibers to keep the carrying capabilities even after attending peak strength. That's in fact in a quick, and I apologize because I don't have time to explain more. That's what I have briefly in my research. I appreciate your listening, and please let me know if you have any question.
Thank you, Dr. Azavi. Just to keep it in the record, let me ask this question. Do you think it's going to increase the cost of production when you include these steel fibers? It's not going to be too much, right?
And yes, Dr. Rajab. In fact, the steel fiber is not expensive. It's cheap everywhere, not here in US, also in Turkey and everywhere is not expensive. Also, the mixing is easy. Yes, it provide 1.5% or sometimes more than 1.5% will decrease the workability, make the work a little bit hard. But still, they have additives. They can improve the workability.
Yeah, but they can use additives for that, and it's for sure that it's actually providing ductility, which is very important. So it's a pretty good work. Why didn't you use circumferential strain gauges to provide maybe more data so that you could calculate Poisson ratio as well? Another work.
You are right. I just put in my mind to find the modulus of elasticity at that time, but still, I have to also.
No, you collected lots of data over there, so you would have included a little bit more, and then now you had another property which is very important also. Next time when you have more students, it's going to be another one.
No, in fact, I did this one by myself, honestly. Without too much help. And as you mentioned, if I provide strain gauge to give me the lateral displacement, I should have channeled to the software.
Yes.
Because each strain should be connected to the software itself.
Yeah.
That's why, at that time, I don't feel the channels are working. All the channels in the software are working. I just keep, some strain gauges, which give me good results.
Good. Yes, it's pretty good. Yeah. Thank you, Dr. Azavi.
Thank you, Dr. Rajab.
Let's go ahead with the next one.
Okay, so what I have the next one?
Don't you have your coffee ready right next to you so you can sip your coffee at the same time?
You are right. So do you have, this is...
you just did that.
I want to just check what I have it here. So did you see the other one?
It's on the left-hand side, experimental investigation. Maybe that's right there.
I should share which one I should share.
Whichever you like.
Yeah.
No, it's numerical now. Numerical simulation.
Now, which one you see, Dr. Rajab?
I see numerical simulation. Well, it's the same thing.
No. This one. Did you see this one?
It's the same thing that I see now.
Okay. Let me stop sharing this one.
Stop sharing it, and then let's get another one.
To the other one.
It's still the same thing.
Oh, okay. So I will close that one. Then I have just this one. You are right. Yeah, I'm sorry. I will.
No problem.
Yeah.
We have time. We are the last one.
Okay. You are busy today. I know everybody busy.
Yeah, we are. This is the last session, so we have all the time available to us.
So did you see the experimental investigation of concrete breakout strain?
Yes. Yeah, this is the one. Yeah, okay.
Yes, sir. So the second research, we have it in our list. is the experimental investigation of concrete
Yes.
breakout strength of post-installed anchors within fiber reinforced concrete. In fact, I did this research with my colleague Travis at the University of Texas, and we try to what we try to find from this research. We need to see how much the effect of micro synthetic fibers on concrete breakout of post-installed anchor bolts. The ACI code, in fact, doesn't provide us, the ACI code 3.18 doesn't provide us enough information about anchoring bolts, the strength of anchoring bolts with concrete with fibers. They just give us in chapter 17 how we can calculate the anchor strength by using the normal concrete. Now we are trying to make this attempt and to provide some information for that. How much will fiber reinforce effect on tensile capacity of post-installed anchors? How will the fiber reinforcement affect on breakout area? And can an inclusion fibers with concrete improve for example, the guardrail anchoring strength as an application? What we did here in this research, we used post-installed anchored. So, which is mainly, we need it in bridges, in guardrail, we use post-installed, we need it in fixing pumps or equipments with the foundation. So the outline of the research is the identify experimentally the effects of micro synthetic fibers on concrete breakout of post-installed anchor bolts, heavy duty galvanized screw anchors with a finished hex head were installed within concrete specimen of different amount of polypropylene fibers. In fact, we used here polypropylene fibers, not steel fibers, just to see what is the difference between steel and synthetic fibers. This slide shows us the failure mode we expect with anchor bolt. So any anchor bolt with tension, we expect either we have steel failure, the anchor bolt itself will be failed by yielding if we have good anchorage between anchor bolt and concrete, or we have concrete breakout failure, and this is the common failure we have it in industry. The other one, we have pull out if we don't have enough bond, enough anchorage, enough development length for this anchor, so we expect to have pull out. The most common failure, as I mentioned, is the second one, which is concrete breakout. The ACI code the ACI code 3.49 give us formula how to calculate the ultimate tensile strength of anchors. But this is without fibers. This is for normal concrete. Also, the ACI code 3.18.19 in chapter 17 give us another formula. It is modified and give us results more accurate than the other one. They consider a concrete breakout prism with angle approximate 35 degrees. This formula could be used for concrete, plain concrete, to find the ultimate tensile strength of anchors. But as we see, it is without fiber. That's why we need to find some formulation, some experiments to find the anchor, the tensile strength of anchors with fibers. 4 mixed we prepared at the lab here at the University of Texas. One mixed with 0 fiber, the other mixed with 0.5% fiber by volume. And as I mentioned, this is polypropylene fiber, synthetic fibers. The other third mix is 1 and the fourth mix is 1.5% fiber. This is the fiber we used. We ordered it here from manufacturer here in US. We use the master fiber, and these are the properties of these fiber we used. These are the formwork we already start doing at our lab. This is the lab yard, and this is the building of the lab, the OTA. So we prepared different samples. This is the Travis, my colleague. He already worked on the formwork. We try to prepare the specimens ready to cast concrete, and we start casting, in fact, concrete. We hired a volumetric truck here. This volumetric mixing truck has all the component inside, has gravel, sand, cement, and also we give them the fibers. These are the fibers, and they mix it at the same time based on the mix design we already give them, and they provide us concrete, mixed concrete with any percent of fiber. So the concrete mix on site here, as we see, and we have our specimens ready for cylinders, beams, and also for the slump test. During the cast day, first of all, we start also calculating and checking the slump just to make sure the slump within the limits. As we see, this is a casting day. Then we start cast our specimens. We prepare our samples here, as we see, based on the ASTM for compression, for tensile, and for a flexure. Also, I join them to during the casting day. Just make sure everything going correctly. These are the beams used for a flexural test. After finishing the casting of our samples, we put it also stored in the curing room. 2 days, 48 hours, we remove this formwork, then we store it in the curing room. After 28 days, we start doing tests. So we start with compression test, as we see, based on the ASTM C39. We also finish the separate tensile test based on the ASTM 496, and also for a flexural test, as we see here. This is one sample for 1.5% steel fiber, synthetic, as we see. This is synthetic fibers. See, these are the synthetic fibers, not steel fibers. We have the results for compression, for tensile, for modulus of rupture. Yes, the synthetic fibers increase the tensile strength very well, and also the modulus of rupture, but it's not helped that much to increase the compressive strength, which is we don't worry too much about compressive strength of concrete. What we need, in fact, mainly is improve the tensile strength of concrete. This type of anchors we used the dual screw bolt. Also, we ordered from manufacturer here. This type of bolts used in many applications, in guardrails and bridges, in fixing some brackets in existing concrete, also fixing some equipment, pumps for existing concrete. So we use this type of post-installed bolt. This is the typical polar test setup we did. This is our specimen here, and this is the bolt. And we provide some framework here for test setup with hydraulic ram, load cell. Just this load cell will give us the record the reading of the applied tensile load. This is the test we already did. This is our sample, and these are the bolts, and this is the framework we have, and this is the hydraulic ram, and this is the load cell as we mentioned. This is the bolt we installed inside the concrete. Then we start apply tension to these balls, and you will see how much strength can carry, tensile strength, and what is the type of failure, and how much concrete cone diameter, and how much the concrete cone breakout angle here. For more angle means more strength, more capability to resist, more tensile strength. After we test 5 specimens each mixed design. Each mixed design we provide 5 specimens. So for plain concrete, these are the results. We have, as we see, we have big damage area. This is the concrete cone, and the angle, the failure angle was not too much, was just around 20-25, and that's expected because we are using plain concrete without any fiber, so easy to fail. And the failure mode is in concrete breakout. This is another sample. This is another sample also for same mix, and still the angle, the failure angle or breakout angle is not too much. This is the 4th one, and this is the 5th one. Then we take the average for all the 5 specimens. We did also same thing for 0.5%. With 0.5% fiber, as we see, the damaged area is not too much. The breakout angle is a little bit high. The concrete breakout diameter is not too much, as it's just 3 inches. And the ultimate load, the tensile ultimate load, is increased. And we expect that, providing fibers will make the concrete more ductile. The other specimens also for the same percent fiber we tested. We tested 5 specimens and record all the results. Then we go to the other mixed design, which is 1%, and also we record our results. The angle, it's high. In fact, the breaking out angle is high, and the breakout diameter is not too much. This is the 5th specimen for 1.0% fiber, and for the last percent ratio, 1.5% ratio. Also, we see the damage is not too much, and the breaking angle is really high. On some failure, we have it. In fact, we have pull out failure, not concrete breakout, because the concrete is very stiff with 1.5% fiber. That's why we have pull out failure here, not concrete breakout, because we don't have, as you see, we don't have that much damaged area with 1.5%. That means if we provide more fiber ratio, the damage in concrete will be very low, and the dominate failure for the anchor bolt will be by the pull-out test, or if the embedded length is not too much, it will be by breakout. This is this curve shows us increasing this T ratio will reduce the breakout diameter or the damage area diameter, as we see with 1.5. See how much the diameter compare with plain concrete. Also, the failure angle trend, as we see, increase the percent ratio will increase the failure angle. with 1.5%, we have this angle. With 0%, we have low failure angle. Low failure angle means we have more damage, more concrete cone damaged. And this table shows us the ultimate breakout, tensile breakout for different mixed design, and also the other side show us the diameter and the angle table. So as we see, with 0% fiber means we don't have any fiber. This is the angle, the average here, and the diameter we have it's around 8 inches. If we increase the fibers, the diameter decrease, the angle increase, as we see here. The diameter decrease, the angle increase of the concrete breakout, and also the load, as we see, it's increased as the percent of fiber increased also. After that, we take the ACI code and the equation and try to modify it by applying term here, covers adding the fibers itself. So we provide this term here, LF by DF by the steel, by the polypropylene fiber ratio, and try to check this formula and validate it with the experiment results. So this trend show us the results for using the modified CCD method, which is proposed by the ACI code. This is the comparison between the modified CCD method and the experiment. So we have a close agreement between both methods. The main conclusions, fact, we can obtain from this study that the experiments revealed the concrete failure cone angle approach 45 degrees and its diameter reduced as the micro synthetic fiber dosage increase. So more fibers, that will improve the behavior of the concrete breakout. And also addition of fibers and increase the ultimate concrete breakout capacity of the anchor by 29% for every 1% of fiber dosage. Addition of micro synthetic fiber and increase the tensile and the flexural strength of concrete, and the concrete mixture becomes more ductile. The experimental concrete breakout strength result are close to the modified ACI code 31919, which is available in chapter 17. A remarkable improvement of concrete breakout strength in tension allow use fiber reinforced concrete in different applications, such as in bridges as a guardrail anchoring, or in the other applications. Thanks for listening, and let me know please if you have any question.
No, thank you. This was a pretty good presentation. Yeah, the results make sense. Yeah. Well, thanks, Dr. Azavi. Let's go with the next one.
Thank you, Dr. Rajab. I really appreciate your listening, and the others also.
It was very nice experimental work.
Oh, yes.
It's a lot of work, and you don't have any student help.
I know.
Yeah.
But we have to manage ourselves, We have to use our availability, as much as we can. But I try my best to do experiment, honestly. I like experiment work more than the numerical work.
Numerical work, yes.
Yes, sir. So
okay, let's go with the third one.
Yes. I will remove this one, then I can go to the other. Did you see the this?
Yes, investigational breakout strength of anchor in tension with fiber reinforced concrete. Okay. Yes. Okay.
Yes, Dr. Rajab. So this research is going to investigate the concrete breakout strength of anchor in tension within fiber reinforced concrete. I did this research with my colleague also Karthik here at the UTA, and this research investigates experimentally the concrete breakout of cast in place headed stud anchors in tension within fiber reinforced concrete. We use high strength anchors F1554 grade 105 and installed for varying steel fiber dosage for different mixed designs, 0%, 0.5 and 1%. In fact, we are not considering grouping action effect in this study. We make sure that the distance between anchors is enough, so we don't have any grouping action. So this research, as I mentioned, we are using cast in place anchors, not post-installed like what we have in the previous one. And we are using high strength anchors just to make sure we don't have steel failure. Mixing of concrete, also this is the mix design used for our project here. We are using steel fibers here, different types of steel fibers. We get it from the supplier here in US. These are the anchors I ordered, in fact, from the manufacturer, used as anchor bolts, and usually used at the base plates in buildings, many types of applications. We are using cast in place anchor bolts. These are the specifications. It's ASTM F1552, and it's a grade 105. The yield strength is 105 KSI. I use this yield strength just to make sure I don't have any yield failure in the steel itself. I need to failure will be developed in the concrete itself. So we use 0.5 inches diameter with 8 inches length. Also, we ordered heavy hex nets with coupling nets, which is used in this research. This is the framework we proposed. This is the plan, and these are the sections. So we are using one beam and divide it to different pieces here, and we try to install our anchors inside this beam. During the casting day, we already prepared and weighed all the materials required. Then we cast our beams here. As we see, these are the anchors installed already. These are the anchors installed. Also, I was with them during the casting day. We prepared also the beams, cylinders. This is for split tensile. This is for compression test, and these are for modulus of rupture. Check the slump also based on the ASTM C143. Then we start in the cooling room. After 28 days, we start testing these samples for compression test, and this is the result for compression test. In fact, with the steel fiber, we have an increase in the compression strength as we increase the steel ratio. But the remarkable improvement in the tensile strength, as we see here. So the split tensile strength increased around 40% to 112% compared with concrete without any steel fiber. And also we test the modulus of rupture based on ASTM C78, and these are the results. Also, we find there's a remarkable improvement in the modulus of rupture for these specimens. This is the test setup we used based on the ASTM E488. So we have a hydraulic ram with the load cell, and this is the machine. We can use it to apply the tensile force to our anchors, our anchor bolt here. As we mentioned, we are using a headed stud, so we have net at the bottom here just to improve the strength of the anchor bolt against the concrete breakout. We don't need to have any pull-out failure. That's why I used here a head stud at the bottom. I use a net here. These are the results at the testing day. This is for 0% fiber reinforced, and as we see, we have this damaged area. It's a big damaged area here. We have video here. I can show you how we start our test. So we apply tensile force, and this is our anchors as we see, and we apply. We provide extension here and coupler here to provide tensile force. And we see now, I hear the voice of the concrete, cracks here, and as you see, this is the failure, and that's it. The member cannot, the anchor bolt cannot resist more load here. This is the top view. This is the anchor bolt, and these are our failure. As we mentioned, we try to avoid the grouping action. The ACI code says if you provide distance between anchors more than 3 times the embedded length, the grouping action will be not available. So we provide more than 3 times embedded length. These are the failure as we see, and these are the results for 0%. So the average, this bolt can carry 5,794 pounds as a tensile force. Now we go to the other type of mix design by providing 0.5 steel fiber to the concrete mix, and we will see what results we have. Also, I have a video here show 4.5, this is 0.5% fiber, and these are our steel anchors. They behave a little bit different, honestly. The concrete carry more. The breakout cone is not too much, and we don't have pull-out test. That means the concrete behave as a ductile. Even the cracks we have, it is not too much cracks. See, this is 0.5. See how much cracks we have compared with 0% fiber. So we have really good results with 0.5% steel fiber, and the results also improved. The average is 10,000, around 10,000 pounds, and the previous without fiber was 5,000 pounds. With 1% steel fiber, also we notice that the failure is very little here. There is no even concrete to break out, and there is no cone also fail here. Just we have some cracks, and the result doesn't increase too much compared to 0.5%. It's 12,000 compared with 12,000 compared with 10,000, but still I recommend it to use 1% steel fiber with anchor bolt. This is my recommendation. This is the trend show us how the tensile strength increase by increasing steel fiber ratio. So with 1%, the tensile capacity, or we can say the breakout capacity of concrete is 12,000 1,000. With 0.5 is around 10,000. With 0% is 5,700 pound. So just to provide some fibers to the concrete mix, especially in pedestals, in the anchor pedestal zone, that will improve a lot the ultimate tensile capacity, especially if we have uplift, if we have windy area, if we have structural steel building. We have table here show us the average cone diameter and also the angle failure. As we see, the angle is increased if we provide more fiber, and the diameter of the cone decreased as we provide more fiber compared with the plain concrete. These are the results. We have it. The average breakout capacity of concrete in tension, as you see, it's remarkable improvement. This research gives us some conclusions that the concrete breakout strength of anchor in tension increased by 77% of 4.5% steel fiber dosage, and an increase 107% for 1% of steel fiber dosage in comparison with the plain concrete. Also, the failure angle increased, as we see, with increase the dosage of fiber. The failure angle approaches 40 degrees as the dosage of fiber increased to 1%. The diameter of cone of an influence decreased as the dosage of fiber increased also. And I feel, this is very good research. We can use it in our applications.
Yes.
I appreciate your listening, and let me know, please, if you have any questions.
Thank you. It was very good experimental work. So it's obvious that the behavior of the concrete improves by using those fibers addition over there. It's pretty nice. You're sending your reports to Texas DOT, right? Send them to
Yes, I already
Department of Transportation. Yeah.
Yes, I already did, and we work with them for that. Yeah.
Yeah. Thank you.
Hocam,
Okay,
can I ask a question, please?
Sure.
Are they cured, Professor Azzabi?
I mean,
the samples are cured, or?
Oh yes. Once we cast the specimens, we store it after we remove the formwork. We store it in the curing room. We have a curing room.
Oh, okay.
We have it. I think I have a slide here show us. We already put it in the curing room. Dr. Rajab, I think he visited our lab and
yeah, I know.
Not
in this presentation. You already showed that room in the previous two presentations. Not in this one.
Yes, yeah,
but I know that there is a curing room over there, and yes, I know.
Yeah, we have two curing room. In fact, a big curing room in our lab, so we can store our specimens for 28 days, and we can test it after that. Yeah, it's good. Yes.
But the results are very promising.
Yes.
Yes, in fact, I did it by myself, and I watch it with my colleague. In fact, if we need to increase the tensile strength for anchor bolts, any types of anchor bolts, we just need to provide some portion of steel fiber, mix it just with the pedestal, not for the foundation or everything. No, just the pedestal. Maybe the height of this pedestal, maybe 4 feet or 5 feet. That's it. And we will see how much will increase the strength. We don't need to use long bars or high diameter of anchor bolts. No, with reasonable anchor bolts with some portion of steel fibers, that will increase a lot the tensile breakout of the anchor bolts. And this is done experimentally, and I approve it.
Thank you very much, Professor Azzabi. Recep Hocam, I must leave because I have to take the kids from the school.
Yes.
I know.
So it is almost 7. So I have to take them at 7:20. And,
okay, thank you. You can watch the remaining parts from YouTube channels. Yeah, they are already recorded. So they are being recorded anyway, so you can watch them later on.
Thank you very much.
Thank you, Professor Fratias. Thank you.
Thank you for attending. I appreciate your comments.
Yes.
Thank you very much. All the best. Bye-bye.
Bye-bye.
Thank you.
Let's go with the fourth one, Dr. Azzavi.
Yes, Dr. Rajab, I really appreciate your patience, huh?
It's always a pleasure to talk to you, my friend. It's always a pleasure.
Thank you, Dr. Rajab. Thank you. So what we have else? So it's experiment. All are experiments, correct?
Yes.
You like it, I believe.
Always, yeah. I did my PhD also with a lot of experimentations. That's why I like experimental works much better than numerical ones.
Yes, so I just want to share this also with you, Dr. Rajab, and the others. So can you see my screen?
Yes. Shear strength within fiber. Yes.
In fact, this research shows us the experimental investigation of anchors shear strength. So we check, in fact, shear strength, not the tensile strength.
Yes.
Within fiber reinforced cement composite under different loading rate. Also, we did this research at the University of Texas. An investigation was conducted to identify the behavior of fiber reinforced cement composite on the concrete breakout shear strength with a steel stud under different loading rate. We use different types of steel rods here. We are using a steel headed stud, G grade 55. It's carbon steel studs, not like what we have in previous research. In the previous research was high strength steel studs. Here, no, I use grade 55 instead of that because I don't have tensile yield problem. These studs were installed for varying synthetic fiber dosage, also different types of dosage, and also no grooving action effect are considered. This slide shows us the anchor failure modes. For different types of behavior. First anchor mode, failure mode, we have steel failure preceded by concrete spall. So we have steel failure here. If we provide shear at this anchor, we expect we have shear failure at the steel itself. Or we have concrete breakout of anchor far from the free edge. So if we have anchors far from the free edge, we expect to have this type of failure, which is the common. This is the common. When the anchor bolt close to the edge and we apply shear, so we expect we have concrete breakout as we see here. These are the three anchor failure modes. Also, we have our mixed design. This is the synthetic fiber we used in this study. The anchor specifications provided. These the anchors, and these anchors are 55 KSI tensile strength. Also, we have had heavy hex nets we used during the test. These are the specifications of these nets. The compressive strength of the concrete, it's available in this slide. The tensile strength also, it's show that there's an increase in the tensile strength as the percent of fiber it's increased, as we see here. the modulus of rupture also increased. And these are the percent of an increment increased. This is the anchor shield test setup I did in the lab. So I used this machine to provide shear test on these anchors. I see, as we see here, and also I use the LVDT to record the deformation in the anchor bolt. As we see here, this is the LVDT, and this is the anchor bolt, and this is the plate, and this is the load cell. We have it here, and how the load apply. This floor goes up, and this is doesn't move. That's why we provide shear through this plate to this anchor bolt, and this LVDT record how much movement we have in this anchor bolt, like what we have here.
I see.
These images show us more. This is the LVDT, this is the anchor bolt, these are our nets. And all the LVDT, the load cells already connected with the software, the strain smart software record the forces with the strain and the deflection also. This slide also shows us the test setup to check shear for the anchor bolts. These are the software, and these, as you see, these are the channels we connected with the software. I have two channels, just for one for the LVDT and the other one for the load cell, and we can apply the load from here. We can modify the rating load, how much we need. We can apply the load. This is 1.5% synthetic fiber. So after test with 0% synthetic fiber, we have this type of failure. The failure mode, in fact, is a steel failure. We have a steel failure. This anchor bolt failed by shear, honestly, and proceeded by some concrete spalling, as we see. And that is expected as specified in the first or second slide. We expect this type of failure in our specimens. If we provide fiber here, then still the failure mode is a steel failure preceded by concrete spall here. But the area is less than what we have in a plain concrete, the damaged area. With 1% fiber, as we see here, we don't have that much damage in concrete, and mainly we have failed in the steel fiber, in the steel anchor by shear. With 1% we don't have, in fact, any damage with concrete, just the small portion around the anchor bolt, but we have here shear failure at the steel itself. The anchor cannot resist more shear. This is the comparison of specimens with different fiber dosage. As we see, this is for 0% fiber, plain concrete. This is 0.5. See, we have big damage area here. With 0.5 we have less. With 1.5 we have less, more or less. With 1.5 normally we don't have concrete damaged. We have small portion around the bar itself. These are the results we already gathered from the experiment. Providing more fiber dosage will increase the failure load, as we see. With the 0%, we have around 24,000 pounds. With 1%, we have we have around 6,500 pound. With the 1% fiber, for some reason, we have the highest failure load. And I can say that is because, the synthetic fiber we used, it's really affect on the workability a lot, and that's will affect on the concrete properties itself. So with synthetic fiber, I recommended to go with 1% fiber dosage, not more than 1% fiber. So I don't recommend to go with more than 1% fiber with synthetic fiber. With the steel fiber, yes, we can go more than 1%, but with synthetic, an increased fiber more than 1% will really affect on the workability and its effect on also on the compressive strength. That's what we noticed from the test. This test is done by applying 300 pound per minute loading rate. So it takes some time to finish the test, and this curve show us the results. As we see here, increase the steel fiber will increase the this is the load displacement curve. So increase the fiber will decrease the displacement here. That's what we have it. Also, and this show us the test specimen with different loading. This is for 750 pound per minute. So we increase the rate from 300 pound per minute to 750 pound per minute, just to see if we change the loading rate, what's happened, is the failure load will be changed or not. And also we did same thing for the other specimens. We conclude that this is for 300 pound per minute loading rate, and this curve for 750 pound per minute loading rate. And as we see, in increasing the loading rate will decrease the strength. As we see, will decrease the strength. So, and that's expected. The high loading rate will not give us that much strength, and also will increase the displacement, as we see. With low loading rate, improve the strength, and also reduce the displacement at the anchor bolts. We did also for the other specimens, which is 1% fiber for both loading rates, as we see. So high loading rate, reduce the strength. Slow loading rate, increase the strength and reduce the displacement. And these are the results we obtained from the experiment. For both loading rate, 300 and 700 pound per minute. And as we see, for example, with the 0.5% steel ratio, 300 pound per minute give us 23,000 pound. 750 give us 18.87 thousand pound. Also for 1%, we did same thing. So increasing the loading rate will reduce the failure load, and also will increase, as we see here, the displacement. The conclusions we can get from this test that increasing the loading rate lead to decreased load failure and an increased anchor ball displacement. Concrete crushing around the anchor balls decreases as the synthetic fiber dosage increased. Anchor shear failure mode depends on the size of the anchor of the concrete cone of the influence. with it depend mainly on the fiber dosage provided. Steel anchors under shear test experience hyper deformation and finally failed by shear associated with concrete spalling around the anchors with low fiber dosage. Concrete mixture become more ductile as synthetic fiber dosage increases and are recommended with 1% fiber synthetic fiber as a percent.
All right. Thank you, Dr. Azavi. Yes, it was.
Thank you, Doctor. I'm sorry for the late, but I just need to cover what I have.
Yeah, no problem. No problem. I just have a question. Why did you increase the loading rate to 750 pounds per minute?
Why I increased the loading rate instead of 300 to 750?
Yeah.
Yeah, in fact, the main target from this research is to see if we increase the loading rate, especially in dynamic force, in pumps, in vibration, sometimes in bridges. So if we increase the loading rate, is that effect on the capacity of the anchor bolt or not? And we noticed that in increasing the loading rate, it's really effect on the capability of the anchor bolt against shear.
How did you come up with that numbers? Why did you choose that number, 750? Why not 500? Why not 800? Why not 1000?
Yeah, you know, we have specifications, the ASTM E488.
Okay.
So we go with these specifications, and these specifications give us some range we can follow.
Oh,
So
I see.
700 pounds per minute.
Good.
It was reasonable for cyclic loading, for dynamic loading. You know, that is why.
Okay, that's very nice. Thank you very much. And I believe you have the last one now.
Yes, Dr. Rajab. I will share it with you right now.
Thank you. Yes, I wish you had some coffee, not just water.
I have it.
Oh, that's good. Oh, great. Continue. Yes. All right, that's great.
I have here a coffee machine.
Oh, that's great.
I have everything.
You're in the office now, right?
I came to the university.
Yes.
I came this morning, you know, because I feel it's better to.
Yeah, that's right.
Once you have a presentation, you know, it goes online, so it's good.
Yeah, that's right. Yes.
Yeah. Yes. So I will go to the last one. So I hope I didn't take too much time, Dr. Rajab.
No. Listen, we have all the time. We are the last one, so we can go as long as we want. Yeah, anchor group now. All right. That's the last one.
Yeah, you have it. You have it.
Yeah, I see. Yeah, I can see that. Yeah. Now this one is about anchor group effects.
In fact, this research is investigate the grouping action. So if we have anchor bolts close each other.
Yeah.
The ACI
less than 3 times the development length, right? Less than 3 times the development length, and then you need to consider the
correct.
group effect.
Yeah, correct. Yeah, the ACI code says if the distance between anchor bolts less than 3 times the development length or the embedded length. In this case, we have a grouping action. The grouping action will affect on the strength of each anchor bolt. So each anchor bolt will if we test it alone, then if we test it within a group, the strength will be different. Now, this research shows us how much grouping effect factor, how much if we have groups, so how much reduction factor and strength will be done. So this research is done by me and by Singh at the University of Texas. And this research will address different items. What is the effect of the anchor grouping action on the concrete breakout strength within steel fiber reinforced concrete, and does the finite element provide results close to the experiment? How does the change in embedded length and change in anchor ball diameter affect the concrete breakout strength? And the outline of this research is to evaluate numerically the necessary modeling constraints and boundary conditions to calibrate and validate the experimental work. So we have experimental work, honestly, and also we have numerical analysis. And also, after finishing the numerical analysis, we have parametric study. The parametric study here show us the effect of change the embedded length and change the anchor bolt diameter, is that will affect on the results or not. These are the experimental results. This is summary of test results from for the compressive tensile strength of concrete. This is just for the concrete properties, and these are the anchor bolts we used. We used steel-headed stud, as we see here. Also, the diameter is 0.5 inches, the length is 8 inches, but the distance between bolts, now we use it 5 inches, less than 3 times the embedded length. So 3 times embedded length is 7.5. We use distance 5 inches just to make sure that we have a grouping action will be developed at this region. The concrete breakout strength comes from the experiment. For plain concrete was 9,000, for 0.5% fiber was 13,000, 1% fiber 16,000 pound, and 1.5% steel fiber we are using here is 16.9 thousand pound or 16.9 kips. The finite element modeling, we use it. We modeled the anchor bolt as a bar element with 0.5 diameter, and also we are using a concrete block element, a solid element for concrete material. These are the material properties for steel.
Dr. Azavi, it's not moving on my screen.
Oh, it doesn't show?
No, it just shows the opening page, the cover page, but I don't see the following slides.
So
I just see here numerical investigation of anchor group effects on concrete breakout strength within steel fiber reinforced concrete. And then Third International Turkish World, October 22, 22nd, 24th by Raad Azavi, presenter Raad Azavi. The opening page, the cover page only. I don't see the following slides.
okay, so can I stop sharing and do it again?
Yes. Yes, please. Yeah, thank you.
Yeah, thanks for letting me know. I want to check what I have here, so I think this should be goes.
Okay. Let's move. Yes, okay, let's move on.
I will move on.
Okay. Oh, now, okay. More.
Oh, okay. Okay, so I can just say it in a quick. So we have this research study the grouping effect on concrete breakout strength. we have experimental results already done, and we need to evaluate these results with the finite element analysis using Abacus software. The experimental results already available for compressive, tensile, and the flexural strength of the concrete. And these are the anchor bolts we use it.
Yes.
We use a steel-headed stud. As we see, we have head at the bottom here, just to increase the concrete breakout strength. And we make sure that the distance between anchor bolts is less than 3 times the embedded length. So we make sure that we have a grouping action at this region. We need to see how much that will affect on the strength of the anchor bolt individually. So if we test one individually, and if we test the same anchor bolt with same properties within a group, so how much that will affect. This is not also available in the ACI code, honestly. They didn't give us reasonable results for the grouping factor. But we tested, and we have an idea now. The experimental results show us the concrete breakout strength in tension for different mix design for 0% steel fiber, 0.5%, 1%, and 1.5% steel fiber. The finite element modeling, we use the bar element for the anchor bolt, and solid element or concrete block for concrete. These are what we have here is the material properties for steel, the yield strength, the modulus of elasticity, and also the Poisson ratio. And this is for concrete damaged plasticity, which is these factors are available as a default in the software itself. And we have here the material properties and test setup, as we see. So this is the test setup. We have it. So we have these 2 anchor bolts, and we provide some frame here, and we test both anchor bolts at the same time. So we apply tension here. This is a load cell. We apply tension, and we test both anchors at the same time, not one anchor at one time. And we will see how much the grouping effect on the strength of the individual anchor bolt. By the way, we have the strength of the anchor bolt individually. We already tested before. So we know how much this anchor can carry, as we see here from this table. So these results are the strength of the anchor bolt individually without any grouping action. So we modeled, we did the modeling in the Abacus here, and this is the numerical assembly. The embedded anchor bolt, as we see here, we modeled inside the concrete unit. We use the displacement control to apply the load. In Abacus, this is the test setup. See, as we see, we have 2 anchor bolts tested at the same time, and we have all these test instruments. We try to match with the modeling, especially the boundary conditions. The creating the mesh was challenge for us, honestly. We tried different mesh sizes. Then we select mesh size 1 inch by 1 inch, because this mesh give us close results between the numerical and the experimental result, as we see. The other meshes, there's a difference between the results. That's why we use mesh size 1 inch by 1 inch, and we modeled our specimen using finite element analysis. Then we run our analysis, and we have these results. So as we see, we have the concave breakout failure around the bolt. This is from the finite element, and it should be matched to what we have it in the actual experiment. So the actual experiment, as we see, we have this grouping action effect, and we have these damaged. It seems like we have one anchor damage in this area, and that's expected. That's what we have it in the finite element also. This is for the plain concrete, so we have huge damaged area here. I see we have a huge damaged area. This is for 0%. This is the experiment, and this is the analysis, finite element analysis. We measured how much. This is for 0.5% ratio steel fiber. So the concave break out failure is a little bit less compared with 0%, and with 1%, it's as you see, the damage is less compared with 0%. The damage is less. For 1.5%, you know, this is the failure, and if you remember, and this is finite element, and if we remember the 1%, 0% fiber, see how much damage we have. Same bolts, same embedded length, same thing. We just increase the steel fiber. Instead of 0%, we provide 1.5% and see how that will improve the performance of the anchor bolt against tensile failure. Then also we did modeling for single anchor bolt, just to see how much it will carry. And these are the results. This is the grouping factor effect. It comes from the experiment. So if we test one anchor, a single anchor, without grouping effect, with the grouping effect, we will see there's a reduction in strength around 0.81. The strength, the grouping effect factor, it's 0.81, means we have reduction in strength around 0.81. If we increase, if we put the steel fibers, we have also a grouping factor ratio available here. Numerically also, we have these results. It's close to the experiment, not same, honestly. We have difference, but that's expected. Usually the numerical analysis will not match exactly to the experiment. We have around 10% difference, which is accepted. So this is for single bars without grouping action, and the other group with grouping action. This is the difference between the numerical and the experimental results, with the percent of fiber and the concave breakout strength. So as you see, increasing fibers will help a lot to increase the concave breakout strength. Okay, also this is another chart show us. We did some parametric study to change the diameter of the anchor bolt and keep the embedded length same. We noticed there is there's no much difference, honestly, if we increase the diameter of the anchor bolt. So if we increase it from 0.5 to 0.75, as we see, there is no much difference in the strength. And the reason behind that, usually the concave breakout, it depends on the development length, honestly, the embedded length, sorry, not on the diameter of the bolt. It's effect, but this effect is not too much. Change the embedded length, its effect If we change the embedded length from 2.5 inch to 3.5, then we will see there is a difference as we see here. Increase the embedded length will increase the strength of the anchor bolt and tension, as we see. See how much it's increased. 2.5 inch embedded length give us 9.7 kips. 3.5 give us 12.4 kips. And increasing the fibers also will increase the strength if we increase the embedded length, as we see here. So more embedded length will help to increase the concrete breakout strength. In general, this research, I feel this is good research because it's really goes and study the effect of grouping action experimentally and also numerically, which is not mentioned in the ACI code. We don't have also numbers of how much grouping effects factor we have to use. But with this study now we have some values we can use it. The nonlinear finite element analysis show a good agreement with the experimental results and also the use of concrete damage plasticity model. This is in Abacus, seems to be the most appropriate for this simulation. Concrete breakout strength increased by 47%, 84%, 92% with respect to plain concrete, as steel fiber reinforced concrete percentages increased from 0.5 to 1.5 respectively. The grouping effect factor for SFRC for 0.51 and 1.5% is 0.8, 0.82, 0.84, and 0.84 also respectively, increasing the embedded length, for example, from 2.5 to 3.5 inches, and increase the breakout strength with these percents, as we see based on the steel fibers provided. For an increase in the diameter of concrete breakout strength, as I mentioned, there's no much difference. As we see, 2.5, 2.74, 3.9, 3.1. This is the increase if we in the tensile breakout strength if we increase the diameter. That's why my recommendation is to increase the embedded length instead of increase the bar diameter if we seeking for more concrete breakout strength. I really apologize for the quick presentation as the time is running out for me, and I appreciate your patience. And
thank you very much. Thank you very much, Dr. Azzavi. Thank you for sharing your research results with us. It was a very nice experimental and also numerical work. I really enjoyed watching your work and your results. And now you have 2 years to prepare more so that we can host you in Antalya, Turkey. Right? New material, new research, and new results. And then hopefully we see you in person, not on Zoom or any other platform anymore. This is not fun. It's also it's good to see you and talk to you, but it's much better to talk to people in person and share some quality time outside. Eat some Turkish food, drink some Turkish coffee. Now we're not able to provide any of it. Sorry. Next.
I know, but it seems everything is perfect. Also I appreciate all your efforts, Dr. Rajab and the others, to communicate with me from the first time up to date. I appreciate your communications. Give me feedback for abstracts, comments. So that's what help me to prepare everything on time.
That's great. That's great. All right, then it's about time to close this session as well. Thank you very much, Dr. Azzavi.